Welcome to Lesson 6 of our A-Level Physics No-Nonsense Lesson Series. And we're going to start by just recapping where we were up to in the last part of the series, the last few lessons. We'd started discovering new particles. We had discovered, as we already knew, the proton, the neutron. Let's spell these right. Proton, the neutron, the electron. We also had the electron neutrino. We had the anti-electron called the positron. And we had the electron antineutrino. Electron antineutrino. That's neutrono. Again, spelling. Always spelling. Neutrino. So those were known about at this stage. We also knew about particles that were responsible for mediating forces. So that's not these particles, it's other things. So these are known particles that behave like matter. At least that's the way it was understood. These are sort of matter or antimatter particles. But then there are known particles that behave like forces. And here there are some mysteries at this stage in the story. We have the photon for the electromagnetic force. We have the W plus and the W minus boson, and yes, the Z0 as well, but I'm not going to write it here. Bosons. And they were for the weak nuclear force. And remember that where we say force, we could also use the word interaction. It means the same thing. And we knew the properties of these. We knew, for example, that photons had 0 mass. Whereas we knew that W minus and W plus protons, one more time, W plus and W minus bosons had actually quite a huge mass. The same sort of mass actually as atoms have. The same mass as a silicon atom, which is odd because these things get emitted from protons and neutrons and other particles. How can you emit something that has more mass than what emits it? That's quite a challenge to get your head around. We also know that this has infinite range, whereas the one with huge mass is a very small range, really small range. Why does it have such a small range? Well, because it's got such a huge mass. The particles, these W plus and W bosons, are what we would call unstable. They decay, as we know, into our electrons and positrons, our neutrinos, and our antineutrinos. These W bosons, they are behaving very differently to how other sorts of particles behave. Because, as I say, they're emitted and they have such huge mass. But their range is about 0.001 femtometers. Now, most forces we think of as pushes and pulls change in momentum by changing velocity, but these W bosons behave in a very different way. Sure, there's pushes and pulls, but they also seem to be converting mass to energy, or vice versa. These forces seem to be changing momentum. These particles that are responsible for these forces seem to be changing momentum. Let's write it in words. Momentum by changing the mass of a particle, rather than just changing velocity. Remember that momentum is mass times velocity, so you can change momentum with either. And remember that energy is equivalent to mass. That's Einstein's famous equation, E equals mc squared. We'll come to that later as well. So that's what we've got so far. But we haven't mentioned yet the strong nuclear force. And this is something of a mystery. Where does the strong nuclear force come into this? I mean, we met the strong nuclear force right at the start of the course, but we don't really know what it is. So let's put a little subtitle here, strong nuclear force. Now, just as the electrostatic force, electromagnetic force are mediated with photons, and the weak nuclear force is mediated with W bosons, what if the strong nuclear force is mediated by a particle as well? And that was the way the thinking went. And so it was proposed that there was a particle that was exchanged in the strong nuclear force. And the proposed particle to mediate this force, the strong nuclear force, was called the pion. And so we had to go look for this particle, this thing called the pion that mediates this force. And in looking for the pion, we found a bunch of other particles, which was not ideal. So how did we look for the pion? Well, we used particle detectors, like cloud chambers, to detect what particles were created when cosmic rays struck the upper atmosphere. So we say used particle detectors, such as cloud chambers, and I've got some videos on my YouTube channel where I look at cloud chambers. Use particle detectors to detect, spell that right, detect particles created when cosmic rays strike atmosphere. And that's happening all the time. So you just got to get lucky with your detector and you'll detect cosmic rays. And what did we discover? Well, we kind of accidentally discovered a few other particles. In doing this, we accidentally discovered the muon. We weren't expecting it. We weren't looking for it. The muon symbol is the Greek letter mu. Now, this thing has the same properties as an electron, except its mass. It's 200 times more massive. Let's write it down here. So it's 200 times more massive. That was not what was expected at all. We also found, quite accidentally, the kaon. Now we're looking for the pion, and we found this kaon. We used the letter K for this. The kaon was unlike anything we had seen before. It was charged, and the first ones that were discovered were charged positively, but they were also charged negatively or even neutral. They had no charge. But with a mass larger than the proposed, let's write the word than correctly, pion, but smaller than a proton. And oddly, they seem to last longer than we thought they should. They had a half-life longer than what we thought they ought to have. Difficult to explain why, but essentially the more massive a particle is, Usually the less stable it is, with exceptions like the proton. But we did discover pions as well. Thank goodness for that. And they are also positively charged, negatively charged, or neutral. And they also had a mass bigger than a muon, just about, but smaller than protons, sort of medium masses as well. Exactly what we expected them to be. So now our collection of particles, we were looking for the particle responsible for the strong nuclear force. Our collection of particles, our zoo of particles, has now grown. The zoo, at this stage, contains the following: protons, neutrons, electrons, positrons, electron neutrinos, electron antineutrinos, muons. We've also got anti-muons. We've got pions of the plus, 0, and minus variety. And we've got kaons of the plus, 0, and minus variety. And if that's not complicated enough, we also have anti-K0 particles. And of course, we've got our friendly photon as well, with our W plus and our W minus and our Z0. Goodness me, that's a lot of particles. When just a few years before, all we had was protons, neutrons, and electrons. And all of a sudden, in trying to understand the forces, the interactions between these particles, we discovered all of these as well. Yikes. But that is definitely not the end of the story. So we keep looking, and we decide that we need to find ways of making our own particles, of creating our own particles. So we developed particle accelerators to accelerate particles, protons. At first it was just electrons actually, and collide them in a detector rather than waiting for the universe to do the collisions for us, to send us those particles, those cosmic rays, to strike the upper atmosphere. So we've now got these detectors and particle accelerators. Now, there's a physicist called 𝗟𝗶H𝗸𝘀 was the guy who predicted the pions, and he was quite happy to have discovered those pions using cosmic rays. But we want to do more, so we started looking for more particles. And we discovered quite a few more, but I'll save that for the next session, because it gets a lot more exciting. Now, this is an important point here. What about the kaons? Because the kaons are a bit odd. Kaons. So kaons don't behave quite like the others. We've discovered some new property. The kaons are what we call strange particles. They're called strange particles. Let's spell it right. Strange particles. Because their half-life seems to be a bit too big. It's still very small, don't get me wrong. The kaon's half-life is still very small. We're not talking years and years here. But they really ought to have decayed much more quickly than they did. So strange particles had a longer than expected, what we call half-life, which you may remember from GCSE level, but just a reminder, half-life is the time it takes for half of the particles to decay. Just a little bit of a reminder there for you. They had this longer than expected half-life it did not fit the trend. It's very odd. When they decayed via the weak interaction. Via the weak interaction. So we're creating these particles. We find these particles that live a little bit too long. We also discover antimatter particles. We discover antineutrinos that correspond to muons, as well as those that correspond to electrons. We discover neutrinos that correspond to the positrons, just like neutrinos that correspond to the anti-muons. We discover all those particles as well. But there are various rules for what we can see. They call them conservation rules. And we're going to go into conservation rules in more detail, certainly later. Conservation rules. But at this point, we start to think, well, what decides which of these particles from this zoo we get? What decides what's actually possible to be created? We discover a few rules, and I'll share a few of them now before we come back to conservation rules in a later topic. So it turns out that energy is not always conserved. Not really, but energy, mass, or mass energy and mass together is always conserved. There's an equivalence between energy and mass using this equation. You can convert energy to mass and mass to energy, but you can't actually create energy without destroying mass. But we did discover that momentum was always conserved. Nothing broke this rule. That's why things like neutrinos were necessary. That's why you get 2 photons emitted in an annihilation event, or even 2 particles, an electron and a positron, emitted when there is a pair production event. We've seen those in an earlier lesson. Charge also always seemed to be conserved. And what other properties did particles have? Well, that was something of the question. What other properties did they have? And we'll come to that during this topic. So that is a brief introduction as to this topic of quarks and leptons, where we were when we left, and how in trying to find the strong nuclear force mediating particle, we accidentally discovered that the particle zoo was much bigger than we thought. We also have a bunch of particles that I haven't included in this list, which are part of your A-level, like delta particles and sigma particles, but we'll get to all that in a later lesson. So concludes this lesson.